Okay. So this is the delta plus gamma region. So yung tie line, we use the tie line in much the same way as we use the tie lines na available to us sa binary phase diagrams. So siguro pakinggan nyo na lang yung podcast and mas na-explain ko siya doon, no? Pero in brief, no, ito siya, if you have a particular na, for example, itong A, pwede natin gamitin yung tie line that is associated with it. And minsan nakakadulig no, pero ito, if I were to draw it, ito siya. So if it falls in between two tie lines, then you just have to interpolate. Kunwari, nandito yung component nyo, or yung in question. So it's in between these two tie lines right here. So kailangan nyo lang siyang i-drawing ng ganyan. So I can't make it. Parang ganyan. So I hope you get the point. No? Pero in any case, yun yung phase analysis for two-phase region. So parang inverse level rule lang yung gagamitin natin. Same way na ginagamit natin siya sa binary phase diagrams. Okay? So yung relatively new sa inyo is actually the gravity rule. No? So this occurs when you have a three-phase region. So you know that it's a three-phase region if it's a, I don't know, if it's connected, yung apex niya, it has three apex, tapos yung apex niya is connected to parang single phase region. So for example, itong specific na to, itong region na to, or itong gray region dito, this is a three-phase region of beta. So para siyang, if you were to isolate this, para siyang may kumbaga isolated siya na sub-ternary diagram, if you can call it that, no? So meron siyang beta region dyan, may alpha siya, may gamma, and meron siyang delta dyan. So if you want to get a specific, for example, itong B, then you need to use the gravity rule, no? And the gravity rule is given by this equation. Where is the gravity rule? Wait lang. Ito. This is the gravity rule, no? So it's yung X na yung component ni, for example, gusto natin mahanap si delta, and a point B is just equal to BZ over gamma Z. Okay? So ito si point P, no? So if you do the gravity rule, etong length na to over this length will be para siyang inverse level rule lang din, pero using parang itong gravity rule na lines, no? So ito siya, this yung the amount of gamma na meron ka is equal to etong lever na to divided by the entire na itong line na to. Okay? So, medyo inverse lever pa rin siya kasi kung gamma yung, delta yung dinedetermine mo, yung inverse lever yung kukunin mo dito. So, similarly, kung ito naman yung kukunin mo delta pala to. Amount of gamma naman, then it's this lever right here divided by the entire length right here. And if you did it correctly, you should get, dapat, this should add up to 100% to. Ito, tatlong to. Okay? Now, 'di ba usually pag phase analysis tayo, may two parts, yung pag-measure ng amounts and pag-measure ng components. So amounts is just how much of each phase is available, no? So for example, ito, 41% ng delta, 40% ng beta, tapos around 18% na gamma. Okay? Pero in phase analysis, pwede rin kasi natin ma-compute yung compositions, no? So if you want to get the composition, then you just get the composition of the of the apex, no? Or vertices. So for example, itong mga vertex na ito, then you just determine its composition. So for example, you just do yung regular na ternary diagram na identification, no? For example, this is zoomed in, no? Pero kumbaga itong let's look at the gamma, no? So gamma is, ito siya. So that's around, kung component B, it's 20, around 20 something, 27%. Oh, no, sorry. This is 20 and itong next line is 40. So around mga 30 siya is it's a midway point. So 30% nickel, and nickel nga ba yung ano nandito? Oo nga, nickel nga siya. So yun. So whatever is the composition of the vertex, siya yung magiging ano natin, yung um, composition ni mismong gamma. Okay? So parang ang interpretation nito is you have 18% gamma, and that 18% gamma is comprised of 32% chromium, 30% nickel, and 38% Fe. And you can do that for all of the other components. No? Now, another use of the ternary diagrams is instead of phase analysis, pwede actually tayong gumawa ng cooling curve analysis. No? And cooling curve analysis is more useful pagka ang dinidetermine natin is, or pag we're dealing with usually mas ginagamit siya sa pyrometallurgy kasi we are dealing with parang liquid metal, tapos parang how they solidify, no? Although it can also be used for physical metallurgy, and I think I've used ternary diagrams kahit dun sa sa motolite, kasi we dealt with mga ternary na systems, parang lead, tin, and calcium. So we can also look into this para ma-determine kung ano yung solidification behavior, kasi nagme-melt kami ng mga lead alloys nun. So ano yung solidification behavior based on the cooling curve analysis. Okay? So ang the way cooling curve analysis is laid out is it's different from kasi again 2D representation lang tayo, di ba? So if for phase analysis, this is taken at specific na mga cuts, no? So for example, if you have kunwari itong 3D plot na parang ganyan, 3D plot na to, pwede kang mag-take ng mga at different temperatures. Pwede mong i-slice itong 3D image natin, and those 3D images will produce different na as shown in this parang mga isothermal cuts na to. So pwede siya mag-produce ng vastly different na So look at at different temperatures, magkaiba yung itsura ng mga nila ng phase diagram. Okay? Now, instead of looking at the phase analysis, no, kung cooling curves yung concern mo, then we are mostly concerned with the top surface, no. Itong parang we call this as a eutectic surface. Okay? So si eutectic surface, ito yung mas primary concern natin. And if you look at it from the top view, actually pwede natin siyang no. Parang if you've ever dealt with mga this type of parang ano bang term yun? Topographic maps ba itong tawag dito? In this cases, no, kahit nasa top view tayo nakatingin, so in the top view parang ganyan lang siya, kaya natin siya ma-determine by drawing contour plots. No? So contour plots are kung topographic map siya, contour plots usually kung same elevation. No? And in this sense, parang ganun lang din yung kinukuha natin, no? Same elevation, but yung elevation natin is in terms of temperature, kasi yung temperature yung y-axis natin. So same elevation. So technically yung mga contour plots na to is same isothermal siya na mga contour plots. Okay? So parang ganyan. So if you were to parang plot this, we would get something that looks like this, no? Parang ganyan tayo na image wherein merong mga different na contour plots that designate different temperatures, no? And a good example is yung nandito. If you look at the top view, ganito yung makikita natin. Tapos makikita natin na each contour plot dito meron siyang designated na mga temperature, no? So in a way, kaya natin ma-determine kung ano yung na-experience ng metal natin. Alright? So dito, dito tayo. So start tayo with um, kunwari lang meron tayong cooling curve analysis for a particular na metal composition, no? So for example, ang metal composition natin na is X. So i-explain ko na lang din to para mas malinaw, no, kasi this is a relatively new topic. But if you want to learn more, pwede namang I've sent, hindi ko alam kung nakita nyo na class, no? So dun sa Google Chats natin, meron akong sinend na, wait lang, let me pull it out, no? So ito, medyo bibilisan ko lang konti. Pero wait lang, ha. Nasaan ko ba sinend yun? Ito. So I'm not sure if you've seen this class, no? Pero hopefully, meron namang iba na nakakita na nito. So ito, I've listed some important links, no? And ito, nandito pala kayo. So if you want to read more about it, pwede naman panoorin niyo yung full lecture ko from previous sems, no? About ternary diagrams. So wait lang, class. May tumatawag for some reason. Wait lang. Mga 5 minutes class, no? Wait lang, ha. Hello? Ayan, narinig na ba ulit ako? So, yun, ito, pag nakikita nyo, may links naman, no? So, if you want to review the full lecture from last year's, pwede namang i-check nyo to, no? And actually, may ginamit akong tool doon, no? I think ImageJ yung ginamit ko. So, you can download excuse me. So, you can download ImageJ, no? ImageJ is a free software. It's open source. Tapos, pwede nyo i-download siya to para mas maano nyo, no? Mas accurate yung lines na mapoproduce, no? Although you can, if you printed the ternary diagrams, pwede naman i-measure nyo using a ruler, no? Pero sometimes kasi I think most of us are doing digital na digital na work. So kung digital kayo and you want accurate measurements, you can use image chain, no? All right? So let's proceed. So sana ba tayo? So when we do para lang mas ma-imagine nyo to, no? When we do kasi itong cooling curve analysis, actually we are trying to determine kung ano yung parang liquid and solid components. Tama? Parang ganun yung imagination natin. So if you look at a 3D diagram, kunwari ganyan, and let's just say ito yung component natin, no? So meron siyang um, certain A, B, and C na percentage. Okay? So if you draw it from the top side, so for example, ito, let me just estimate. So somewhere dito, kunwari siya. Ayan. So this is from the top, as seen from the top view, no? Pagka dinrawing natin yung cooling curve profile niya, we start with from the top. Tama? Kasi we are working at a temperature higher than the, parang ganyan siya. So we start, anything above this surface is actually liquid, no? Puro liquid nandito. Tama? So begin with liquid, tapos you bring the temperature down. Tapos as you bring the temperature down, papasok ka na dito sa ano natin. So, papasok ka dyan hanggang dumating ka sa room temperature. Now, as you um, go down this temperature line, nagbabago yung kumbaga liquid to solid ratio mo. For example, ito, we try to draw it, no? So, ito siya. From this temperature, iba na yung parang liquid to solid ratio niya. And we use the inverse level rule dito, no? So, this is liquid, solid. So, kunwari, pag bumaba ka, dumadami yung solid, liquid, and so on and so forth. So, parang binary phase diagrams lang din, no? So, kunwari, sa binary phase diagram, di ba ganyan siya? If you start with liquid, and you do very slow cooling, no? Kunwari ganyan. You can always determine kung ano yung composition using the tie lines, no? So, for example, ito yung composition ng, let's just say solid dito, no? Solid, tas liquid to. Kasi this is the liquid plus solid region. So, parang ganyan yan. So, each part dito is a sort of parang a binary eutectic, kumbaga. So, and actually, if you look at the, ano, no? Itong mga nasa edges, these edges are actually binary eutectics, to, no? Yung mga nandito. In any case, parang when you go down the gradient, kumbaga ito, the solid is growing. Ito kasi yung liquid side, liquid. Ayan, solid, liquid, tapos solid, liquid. Parang ganyan. Hanggang dumating ka sa eutectic point wherein magkakaroon siya ng eutectic transformation or such that liquid transforms directly into, if this is solid 1, tapos may solid 2 ka pa dito. So you have solid 1 plus solid 2. So pagka ganyan, if you reach eutectic compositions, diretso na siya, liquid transforms into solid 1 plus solid 2. Tama? Hopefully, you still remember this sort of things, no? Medyo binibilisan ko lang. Pero anyway, so if you look at this one, yung concentration kasi natin ng, kumbaga, if you start with dito, kaya mo ma-determine kung saan doon sa contour plot or sa surface natin unang initially magta-touch yung ano, no, yung X na to. So as you go down, saan siya dito sa surface magta-touch? So yun actually yung X na nandito. Okay? And dito, it touches the 1,000 degree na contour plot. Meaning, nasa 1,000 degrees, doon magsisimula mag-start si formation ng ano. And if I were to draw the side view of this, if I were to take an isoplet dito, no? So I'll take an isoplet, pa ganyan, na-cut. So probably I'll see something that looks like this surface. So wherein ito, this is the 1,000. Tapos dito 900. Tapos dito 800. Nandito yung 11. 11. So hopefully na-imagine nyo siya ng ganyan. So nandito si X. So kumbaga kung top view to, ito side view kunwari ng isoplet na to. You go down, dito magsisimula mag-form si solid. Tama? So as you go down, so for example, kung dumating ka na sa 900, let me make this a little bit clear, no? So pagdating mo dito sa 900, kunwari ganyan, you actually get this amount of solid formation. Ito yung solid mo. Kasi di ba this is the solid, this is the liquid. Tama? So in this case, solid na C. So kunwari C siya. C. So you get this amount of solid C. Tapos, this amount of liquid is still remaining. Tapos as you go down, kunwari 800, tumataas yung yung amount ni solid, tapos si liquid bumababa. Tapos at the same time, pwede mo din ma-compute yung different na ano niya, no, compositions. Kunwari, we can determine the amount, so percentage S, percentage L. Tapos kaya din natin ma-determine kung ano yung percentage of A, B, and C for S, A, B, and C for L. Tama? Okay? So now, ang ano dito is you can go down the gradient, the contour plots, hanggang dumating ka dito sa, kasi if you follow the plots, kaya mo actually ma-determine kung alin yung, kasi following this line, if you follow this line, itong isoplet na to, you are technically following this liquidus line na to. This is a liquidus line sa pag-binary phase diagrams. Pero in ternary, this is a liquidus surface siya kasi parang 3D na kasi siya eh. 2D I mean. Tama? So this is a liquidous surface as seen from the side view of the isoplethal cut, kumbaga, if that makes sense. So it takes a bit of imagination dito, class, no, kasi kailangan may spatial imagination kayo dito para mas fully ma-appreciate nyo yung analogy, kung paano naging analogous ang binary phase diagrams to the ternary phase diagrams, kasi technically they are an analogous lang din talaga yung ano nila, yung parang treatment, kumbaga, on how you find these things, no. So ito, we have this one. Pagka once you reach this point, no, so we call this as a, tawag natin sa mga lines na to, we have this 3 lines here. We call this as eutectic troughs, no. We call them as eutectic troughs. Once you reach a eutectic trough, ang nangyayari kasi is mag-pivot yung ano mo, yung kumbaga yung isopleth mo. Kasi here, puro sea crystals pa lang yung nabubuo, di ba? Kasi kumbaga etong sa, if you look at the 3D, sige po, check natin yung 3D, no? And sige, para mas kamukha siya doon, let me erase. So kunwari dito sa 3D, no, ang ginawa natin is nandito tayo para C tayo. So definitely liquid sa taas, di ba? Once it goes down, pag pumasok siya dito sa surface na to, itong surface, ang actually yun nandito is liquid plus C. Tama? Liquid plus C. So mag-go down siya dyan hanggang nandito na siya. Umabot siya sa point na magta-touch siya dito sa trough natin. Parang ganyan. So up until this point, so from 1,000 up to whatever temperature this is, later makikita natin kung ano temperature, liquid plus C lang talaga. Yung nagpa-precipitate out from the liquid is C. Now once it touches the trough, doon na magsisimula mag-form si A. Okay? So since A is now forming, ang mangyayari is we actually create a parang a pivot point, no? So this point right here, and this is kung 800 to, therefore itong line na to is the 700 line. So ito, I'm guessing maybe 670, mga ganun, 650 ba? Hindi ko kasi kita kung nasaan mahirap i-determine, no, kasi hindi naman equally spaced sila. Ito dito, that's hindi kita yung kung nasaan si anong tawag dito? Si 600 line. Unless of course alam natin kung ano tong eutectic point na to. Ito, this is the triple eutectic point, no? Itong triple eutectic point is the triple eutectic is the lowest point in the liquidous surface na yun. Okay? So, once na narating natin yung temperature na to, and again, let me just estimate to kasi ito, if this is 700, therefore somewhere along baka mga 680 to or 670, mga ganun. So let's just say 670. So at 670 degrees Celsius, you now begin to form particles of A. So nagpo-precipitate out na si A. Now, if you want to go further down the line, no, then ito, kumbaga, if this is 650 yung nandito, 670 kumbaga, then you can also go further down this line right here. Parang ganyan. So meron din siyang 670, 670, 660, 650, 640 hanggang dumating ka dito sa triple eutectic. And hindi ko kasi alam kung ano yung temperature ng triple eutectic na to. So hindi ko, if we know the triple eutectic point, mas madali sanang i-estimate, no? Kung ano yung mga gradations dito, kumbaga, kung paano siya, kung ano yung scaling niya in a way, no? So in any case, if you reach this point, ang nangyayari is yung precipitate A is now being precipitated out, no? And ito dito magpi-pivot na siya kasi dito i-follow mo na kasi yung eutectic trough, no? So from here, kunwari ganyan. So you follow the isopleth, tapos pagdating dito you follow now the ang tawag dito, the eutectic trough. So the eutectic trough will now dictate the new itong isopleth. Okay? So, pagdating dito sa isoplet na 'to, kumbaga gagamitin mo kasi ito yung, composition mo, ito yung parang pivot point mo, parang ganyan. So, this time ang nangyayari diyan is you actually have makikita mo dito, you have this is the percent A, inverse lever pa rin tayo, ta's this is the percent C. So, out of this is still liquid plus solid pa rin 'to 'no. So, this is the liquid and this is the solid, okay? So, out of the yung, solid na na-produce mo dito, meron siyang percent C and meron siyang percent A diyan, okay? So, kung makikita niyo, parang the percent solids is still itong MX line na 'to, this is percent, solid. Tapos yung NXN or NX line is the percent liquid kasi inverse level, 'di ba? If you look at again, you always try to imagine the 3D, no? To the left side, nandito kasi yung parang liquid natin, itong nag-hover sa taas. So to the right side, if you go down, to the right side is the solid. Okay? So ito, nandito tayo. So you compute for MX and MN. Tapos ngayon, yung percent A mo na that is present in the solid crystals is etong line na to. So you need to, um, wait lang. Tama. Etong proportion na to. This is percent A. Tapos yung percent C is this line right here. Which makes sense, no? Kasi yung solids mo kasi nagta-travel along this line lang naman. Tama? So if it travels along this line, the liquid is traveling along this line dahil sa yung kumbaga yung endpoints ng tie line natin. This is still a sort of tie line pa rin, no? So yung endpoint ng tie line na to is yung first endpoint is traveling along the eutectic trough. Yung endpoint ng second yung endpoint yung other endpoint ng tie line natin is traveling along um, this AC line right here. Okay? So, if it were traveling, kunwari, kung nandito siya, then you would have a different, no? Kasi, baga may A ka, may C ka, may B ka. Tama? Pero since dito lang siya, so it's just A and C. Similarly, kung nandito ka lang din, this is just B and C. Tapos dito, binary lang din siya, this is just A and B. May tanong si Joanna dito. Joanna, can you expand on your question? Ang tanong niya is, kapag isoplet, two components lang yung makikita, then balance na lang yung third. What do you mean by this, Joanna? Yung sa percent solids ba? Percent liquids?
Yes, sir. Good afternoon po. Since
Oo.
kanina, sir, parang na-visualize po na yung isoplet is parang plain
Mm.
cutting na patayo, sir. So,
Oo.
ang naisip ko po, since yung mga drawing po, ganun siya, patayo,
Mm.
di, can you show pala, sir, dito po sa isothermal cut na ito?
Pagka
Kung,
ganito na.
ano po itsura ng isoplet? Yan, sir.
Yung isoplet niya is, pwede natin ipakita dito dito, no? So, let me erase ulit. So, para ang mangyayari dito is, baka mas malinaw kung pula, no? Parang nandito na siya. So, dito siya nag-start, tapos ganyan. So, parang ganyan kunwari, ang isoplet cut natin. So, um, kaya mo ma-determine yung tie lines niya will be something that looks like this, no? Nandito na yung mga tie lines niya. Tama? Pag ganyan na yung tie line. Parang ganyan. Kasi nandito na yung ano mo. So ito, parang kino-consider mo lang na if I were to draw the side view, no? So kunwari ganyan. So kunwari ito yung the ternary eutectic. So parang ito, this is actually our A plus C line. Tapos dito, kino-compute na natin yung liquid natin. And the liquid can have an A, B, and C. Tama? Kasi nandito siya sa loob eh. Pero etong line na to is touching this ano no, nandito kasi sa edge na to which only contains A and C. So kumbaga A and C line lang siya. But take note that as you go down the trough, nagmo-move kasi itong A and C line. So if I were to draw a progression, no? So kunwari ganyan. So kunwari nag-move down ka pa papunta na sa ternary eutectic, no? So ang mangyayari is parang ganyan na yung surface mo. Parang nandito na yung isoplet mo. Parang ganyan. So kumbaga parang siyang nagto-twist or nagpe-pivot parati. Pero yung if you look at the side view, parati siyang A plus C lang siya. And that A plus C is changing because it's moving from this point to this point. Hanggang dumating siya dyan. So A plus C is moving. So ang siguro nalilito lang sa tanong mo sa what you mean by balance is because yung solids mo, definitely si solids is only composed of A plus C. Si liquid, pwede siya magkaroon ng A, B, and C. And to determine the A, B, and C of the liquid, hanapin mo siya sa whichever point it is right now. So for example, ito, percent %C. Then, hanapin mo tong point na to using the way we plot, the way we plot ternary diagram. So meron siyang C component, tama, ito yung C component niya, meron siyang, let me draw parallel line. Oops.
Mas gets ko na po, sir. Bali, etong technique po na ginagawa niyo, sir, gravity rule po tawag. Ay, ano?
Hindi naman gravity rule, pero yung parang usual plotting natin, yung parang yung tinuro dito. Ito, yung parang ganyan.
Ano po tawag dyan, sir?
Hindi ko alam ano tawag.
Okay,
Pero
okay.
this is just the way we plot the ternary diagram. Wala kasi siyang, kumbaga, gaganon yung graph talaga ni ternary. It's a equilateral plot kasi siya. So,
Yes,
yung,
sir.
yung gravity kasi is more of determining three components, yung amounts ng three components, while this one is determining percentage of those components. So hindi siya amounts, more of components siya. And
Okay, sir.
and by the way, class, kailangan yung i-differentiate talaga ng dalawang to. Pag sinabing amounts, it's different from composition. Composition pala yung term na hinanap ko. So ito, again, ito for composition to, tapos amounts, usually we use either gravity rule or tie lines. Okay? Sana mas malinaw 'yon. Kung may follow-up, okay lang. So, probably kasi medyo mahirap pala tong topic na to, no? So, konti na lang yung ipapakita ko sa ang topic kasi natin for today dapat is nucleation and growth kasi yun actually yung wala pa tayong pero I could probably set up a na lang, gagawa na lang ako ng separate podcast for it para pwede nyo siyang balikan. Okay? Pero okay, so once na nandito na tayo and if may naisip pa kayo, just siguro pa kayo, nag-iisip pa kayo ng mga tanong, no? So, huwag kayong mahiya magtanong para mas maintindihan natin yung topic na to. So, okay? So, once you reach the isoplet, go down tayo sa line, tapos hanggang pumunta tayo sa eutectic, wherein kapag nasa eutectic ka na, then obviously, yun na yung endpoint, no? Na kasi from the eutectic point, para siyang yung binary eutectic lang din na the from the eutectic point, diretso siya from the liquid, we will produce solid 1 plus solid 2. Okay? So, try natin. Mayroon bang isang example dito? Cooling curve analysis. Ito. Ayan, meron namang example pala ito. You can view these examples para mas maintindihan nyo kung anong nangyayari. So, notice how always ginagamit si composition. Kung ano yung composition niya, siya parati yung pivot point, no? Hanggang dumating ka sa natin, sa eutectic point. Tapos, this is measuring. Wait. the liquid. Gravity rule actually yung ginamit niya dito for the liquid. I think it should give you the same. So let's try to ano no. Wait lang class ah. Mhm. Yep, it should be the same kung nag-gravity rule kayo or not. Kasi let's try to do it, ano no. If you look at this, this is percent %C. Tapos yung percent B is this one right here. Tapos percent %A is this one. Parang ganun. So if we try to estimate that this is wala kasi akong markings. Pero if this is 50 kalahati, 50. So this is 25 sorry. 50, 10, 20, 30, 40. So ang compute percent A is around 38. Off lang ako konti. So baka 38. Tama. You can still compute it that way, no? Pwedeng gravity rule. So tama ka pala, Joanna, no? You can do gravity rule to compute for the liquid composition. Pero pwede rin yung usual na plotting lang, no? Using kumbaga yung equilateral triangles natin. So you can do that as well. It should give you the same answer. Okay. All right. So, meron pa bang questions about this cooling curve analysis sa ternary?
Thank you, sir, dun sa clarification.
Okay. Alam ba natin ng isa pang example? Maybe I can provide another example na para mas makita nyo. Pero maybe I can show you. Hindi ko alam kung makikita nyo. Kailangan. I can show you a more complicated, no? Bismuth. Anong ulit yan? Kalimutan ko. Wait lang. Let me show you kasi Figo, para hindi kayo maggulat masyado, no? Sa other phases diagrams. Ito. Kailangan ko ipakita to. Ito. Para lang mapakita ko kasi yung pinakita kong example medyo simple lang siya, no, na parang isa lang yung ternary eutectic natin. Tapos meron tayong 3 eutectic troughs lang natin. Pero yung mga real world na alloys natin is more complicated than that. So you can clearly see it with this one. This is a lead tin bismuth na na phase diagram. So if you look at it, meron tayong several na eutectic, ternary eutectic, and meron pala dito 3 ata. This is 1, this is 2. No, dalawa lang pala. 1 and 2. So as you can see, there are arrows pointing to different na ternary eutectics. No? So ito, if you can look at this, yung arrow na to papunta dyan, tapos itong arrow na to papunta dyan, at ito papunta dyan. So I'm looking at this, and ito ata yung pinakamababang point. So ito yung pinaka lowest point ng ternary eutectic na to. So you can see the direction of the arrow, no, and that will indicate whether kung saan ka papunta pagka nag-pivot ka na. So let's just say na nandyan ka, tapos ito yung isoplet natin kunwari. Create an isoplet, tapos nandito tayo. So once we touch this eutectic trough, i-follow natin yung direction ng arrow, no. So for example, if the arrow states na papunta tayo diyan, therefore kung magpi-pivot tayo, dapat pa ganyan. So parang ganyan. Kasi papunta ang arrow dyan. So similarly, if you have something that looks like, for example, nandito ka, so ganyan ka dapat dito. So pag ganyan, tapos once na na-reach mo na to, pag nag-pivot ka, pag ganyan dapat. And tapos hanggang ganyan, so on and so forth. Okay? Hanggang ma-reach mo to. Tapos if kaya pa mag-follow ng arrow, ipa-follow mo yung arrow na yun. Right? So expect na sa exams usually mas ganito yung ibibigay namin, no, na mas complicated na as opposed to yung simple lang. Pero not too complicated naman. Baka ito yung ibigay namin specifically or maghahanap pa kami ng iba pang ternary phase diagram. But this phase diagram is maganda siya kasi it's complicated pero not too complicated as compared to the other phase diagrams, no. All right? So, I think para mas maintindihan nyo talaga and fully appreciate, maybe you can watch the yung previous na video, yung sa natin, sa link na to para sorry, mali pala. Yung sa link na to, so please check ito ternary diagram. Mas na ina-explain ko in detail yung yung methodology doon. So ang tip ko at ipanoorin nyo na lang in 1.5 times na speed kasi baka medyo mabagal ako magsalita, no. So you can watch it. Saan ba ako nag-compute? Most likely nandito na ako nung nagko-compute ako. Yan, this is a lead tin bismuth tin siya na example. Ayan. Hopefully mas magigets nyo pag pinanood to, no. Right? So, balik tayo dun sa Okay, so are there any other questions sa ternary or other lessons? Tapos pwedeng yung remaining 30 minutes ko na lang gamitin pang discuss sa natin, yung solidification, specifically yung nucleation and growth, no? Kasi yun yung medyo kulang. Alright, so I think wala nang ibang nagtatanong. So let's proceed with solidification. So, we can look into, pero may correction dito, may nakita kong correction kanina. So, I'll correct it as soon as I can. No? So ito, this is solidification kasi dapat in our schedule, last week yung yung phase diagrams, phase equilibrium, tas ngayon yung solidification. No? Medyo mas mabilis yung parang flow ng SEM na to. But in any case, i-adjust na lang namin, no, yung parang level of difficulty. We will adjust it with the pace of the SEM, no. Pero ito, this is the solidification part, and in this lesson specifically i-address ko yung ano no, yung how nucleation and growth works. And I'm pretty sure most of you have heard of the term before, no, yung nucleation and growth. And gusto ko lang i-emphasize na si nucleation and growth is sort of medyo universal siya na concept, no, because it not only applies to solidification alone. Kahit sa mga different na aspects, no, kunwari dislocation, dislocations also have nucleation and growth na mechanics. Tapos kahit yung mga kunwari failure, so creep failure, or yung creep failure also has a nucleation and growth na mechanism. So nucleation and growth is fairly universal, no, and it is not only specific to solidification, no. So but in this lesson, mas ano no, focus tayo sa nucleation and growth in terms of in the perspective of solidification. Okay, so we study solidification, the mechanisms involved in solidification, because um, ito yung when we are trying to fabricate metals, no, usually it always begins with a casting process, no, regardless of kung gaano complicated yung process. At some point, dapat kinast yung metal, no, kasi you can only achieve certain alloy specifications pagka if you do precise alloying, no, and alloying can only be done through as far as I know, no, alloying can only be done through melting, refining, tapos parang and adjusting the different components doon sa alloys na yun. And when you have adjusted, kapag properly alloy ka na, tsaka mo ikakast into the different materials. So pwedeng hindi mo i-cast directly into the product, pero you will still need to at the very least cast it, no, to probably an ingot. Tapos yung ingot, yun yung pwedeng i-further manipulate, no. So pwede ring or any other type of raw material, usually nakakast yun, no. So in that sense, sobrang ano no, we can think of yung cast na microstructure as a baseline microstructure. So yung pinaka-initial na microstructure na nakikita natin sa metals, no? So it's important to know how those microstructures develop, no? And bukod doon, apart from casting, no, we can also see yung solidification come into play when we talk about ano no, yung kunwari mga welding processes. Welding process is a type of joining process, and the way it works is yung two metals that are to be joined will be locally melted, and from that local melting magkakaroon ka ng ano no, yung changes in microstructure, kasi magme-melt siya, tapos mag re resolidify siya, and that resolidifications would have a huge impact on the ano no, on the mechanical properties. And in fact, sa mga welding, no, welding joints are one of the ano no, things that really need to be looked into, no, when we talk about parang strength of different structures, no, lalo na pag welded yung structure. So it's important that we know how they develop, and to understand how they develop, kailangan natin na may deep understanding tayo of nucleation and growth, no. So you've heard about nucleation. So nucleation is just when this is the initial stage of the solidification process, wherein yung from the liquid na metal nagbibigin to precipitate out, or nagbibigin to form ng mga crystals that are nucleation sites or nuclei that eventually become stable enough for you to have growth, no. And when you have growth, doon na nagkakaroon ng kung meron na tayong growth sa ating ano, wait lang. Iba ata yung pinapakita ko sa screen. Ito pala dapat. So when you have growth, no, doon na nag eventually mabubuo yung final microstructure natin. So if I were to parang illustrate it simply, no, parang you have nucleation, where you have itong mga nuclei na na-form. Tapos from the nuclei, itong mga nuclei na to, if they become stable enough, magkakaroon siya ng growth. So you have something that looks like that. Tapos eventually it will grow to a large enough size such that magmi-meet sila with the boundaries of the growing grains. So in this sense, grains na sila, no? So magiging ganyan siya. So from here, nuclei pa lang, they grow into large enough grains. Tapos yung grains natin eventually, they will finalize the solidification process until all the remaining liquids, so kunwari liquid to, is has precipitated or has recrystallized into the final microstructure, no? So parang ganun yung ano niya, pattern niya. Okay? So let's talk about nucleation first. Nucleation is can be classified into two categories, no? So meron tayong tinatawag na homogeneous nucleation, and meron tayong tinatawag na heterogeneous nucleation. So familiar ba kayo sa two terms na to? Na I'm pretty sure narinig niyo na 'to, no? So if I were to ask you, ano yung ah, ay, ulit. Tama ba? May comment si Mark. Yung take home screen pa rin ba nakikita sa screen or nag-iba na? Take home exam, I mean. Okay na. Kasi thank you for the feedback, Mark. So, familiar kayo sa homogeneous and heterogeneous nucleation, no? So if I were to ask you, alin yung tingin nyo mas mabilis dito? Homogeneous or heterogeneous? From your understanding of nucleation from MetE176. Ano na lang tayo kasi baka nahihiya kayo. Drop an emoji na lang. Parang thumbs up for heterogeneous. Tapos peace sign for heterogeneous. Thumbs up homogeneous. Peace sign sa heterogeneous. May mga sumagot. May mga hindi pa sure. So maraming sumagot ng homogeneous, no? Okay. So, actually, as yung sagot is heterogeneous, no? Ito yung mas mabilis. So it's faster because and I'll explain this in more detail now. Pero basically, homogeneous is when you have nucleation that starts or that begins from the pure phase or the pure alloy. Tapos from the liquid magbibigin yung solidification process natin, no? So without the aid of any external surface. So for example, ito, if you look at something like this, itong mga nandito sa gitna, that is homogeneous nucleation, no? Now, heterogeneous nucleation occurs when you begin the nuclei formation dito sa with the aid of external surfaces, no? So, kunwari dito sa mold walls natin. So, if this is the mold, so if it begins with at the mold walls, then that's heterogeneous nucleation, no? Kasi meron kang aid ng external surface. So, external surface could be could is not necessarily just the molds, no? So sometimes, for example, in some alloys, no, dinadagdagan natin ng mga additives yung metals natin, and those additives acts as nucleation sites, or sometimes they are called inoculants, no? So in that sense, ang nangyayari is yung nucleation natin is aided by the presence of external surfaces, which makes it heterogeneous in nature, no? Okay? So to begin, let's imagine homogeneous nucleation lang muna, no? And to better imagine this, kailangan medyo tandaan niyo yung MetE176, no, or thermodynamics. So this was discussed in some details sa no, sa surface thermodynamics. So hopefully kung hindi niyo maalala, tayo niyo balikan yung notes niyo, baka mas make sense siya. Pero basically, when you have a I don't know, if you remember delta G, ang pinaka takeaway natin do from MetE176 is that the more negative the delta G is, the more spontaneous it is, or the more favorable the reaction will be. And in this sense, dapat we are looking at, for example, if we are looking at a reaction that involves liquid to solid. Tama? So for this to be para maging ano to, no, favorable, dapat ang condition, ang normal conditions is that if everything is kept the same, no, or normal, then dapat yung temperature natin should be lower than the melting point. Ano, if it's lower, then we are sure na the favorable condition is, or yung mas energetically favorable is si solid. Tama, kasi siya yung mas lower na delta G. And in fact, may dito yung may correction, no, and I'll edit this. Dapat may negative to, no. This should have a negative because yung free energy associated with the transformation from liquid to solid given by this delta GB. This is, we call this as the volume free energy, no? Volume free energy. So, ibig sabihin ng volume free energy is that ito yung Gibbs free energy per unit volume ng transformation from liquid to solid. So it's negative because if the melting point is if you are at a temperature lower than the melting point, then energetically mas favorable na mag-produce ka ng solids. So if we have something that looks like this, na meron kang liquid tapos may solid ka, if we were to grow the solid, then increase of the volume of the solid will decrease the free energy kasi parang from liquid mas dumadami yung volume ng solid mo. Okay? So kung mas dumadami yung volume ng solid, mas bumababa lalo yung free energy ng overall free energy natin, kumbaga. So the volume free energy is multiplied by the, since this is volume per volume to, multiply natin by the volume of the etong sphere na to, no? And the assumption is sphere siya kasi again in nature, no, we always tend to, or nature always tends to minimize the surface free energy, no? And the sphere is the lowest volume to surface area, has the lowest volume to surface area ratio, or highest, I should say, volume to surface area ratio. Okay? So this is the first component of the free energy associated with the transformation from liquid to solid. And dito, this is the negative component, no, yung volume free energy. Now, from what we learned with from surface free energy or surface thermodynamics is that pagka nagka-create tayo ng new surfaces, and technically this is a new surface, no, kasi this is a, pagka nag-produce ka ng solid, meron kang magiging interface between the solid and the liquid. So that becomes a new surface, no? So when you increase the volume, you also increase the surface free energy. Tama? So meron kang positive component doon. So it becomes a sort of balancing act, no, na parang on one hand, si volume free energy is lowering the overall free energy by creation of the solid, by growing the solid. Pero at the same time, by growing the solid, you are increasing the surface free energy. So making the delta G more positive, no? So pagka ganyan, alin yung masusunod? Kasi paano pag ganyan? Magiging spontaneous ba yung reaction or magiging non-spontaneous ba yung reaction? So it depends on yung magnitudes ng dalawang to, no? If this is more negative than this part right here, then obviously magiging spontaneous siya. If this is more has a higher magnitude than this part right here, then magiging more positive yung delta G, making it non-spontaneous, no? Right? So therefore, dito, we can actually, since it's all in terms of R, no? Ito, if you look at it, this is a constant or a material, a thermodynamic property din to. And if you remember free energy, no, it's measured in gamma. This can be thought of as surface tension or surface free energy. Usually surface tension refers to liquids, surface free energy refers to solids, but they are more or less interchangeable, no? And since this is a surface quantity, multiply natin on a per surface to, tama, I hope you still remember, no? Per surface kasi to, per surface area. So, multiply natin siya by the surface area, and 4 pi r squared is just the surface area of a sphere, no? Okay? So, ang gagawin natin is, if you compute for this, if you put this in terms of R, you will have a graph that looks like this, no? Wherein you plot free energy versus the radius. And you will find out that, again, the surface free energy increases, itong red line na to, it increases the overall value. Pero the volume free energy decreases the overall value. So if you get the parang average of, or if you get the sum of these two, itong yung total, you will get a graph that looks like this, no? And you'll notice, para siyang, this is a hill, no? And this is what This is medyo common to sa mga chemistry lessons natin, no? And this is what we call as a activation energy. Okay? So this is the activation energy actually of producing a stable nuclei. Okay? So for solidification to occur. So you can see that from the delta G, we call this as delta G star, no? So yun yung required free energy para makapag-produce ka ng stable nuclei. So this is saying that the way it works kasi is if you have, di ba, mga liquid natin, kunwari liquid siya, tapos ito yung solid natin. Yung mga atoms ng liquid is free flowing siya, no? Parang if it's a liquid metal, free flowing siya, pero once it comes together to form the crystal structure, kunwari may pattern na siya na ganyan. Pag naging ano na siya, crystal structure na siya, magiging solid na siya, right? So there is a certain radius where we consider this as a stable nuclei. No, anything less than that radius means that it can, kunwari nag-come together na tong ano na to. Kunwari may ganyan na, no, may certain amount of atoms na nag-come together, pero hindi siya large enough such that na stable na siya. So actually ito, pwede pa siya mag-redissolve into liquid to solid. So anything before this, so kung R is less than R star, you can expect na reversible pa yung reaction, no? Parang ganyan. Na parang yung liquid can turn to solid, pero yung solid na yun can revert back into liquid, redissolve lang din siya. You will have to require, or it is required na ma-overcome mo yung activation energy na once na kunwari nandito ka na, once na lumagpas ka na sa critical R star na to, itong associated R value of that delta G star, then you can be sure na continuously mag-grow na yung ano mo kasi it will continuously go downhill na from here. Okay? So continuously mag-grow na yung grain mo. So you need to overcome this activation energy and it has an associated R star. So ang tawag natin dyan is the critical radius, no? So dito, we can easily compute for this, no, kasi if you notice in terms of R sila, so if you get dg over dr, and di ba ganun natin usually kinukuha yung maximum, di ba? So for example, kukunin natin yung slope that is equal to 0 siya. So parang if this were y over x, if you have a graph that looks like this, kung gusto mo makuha tong mga local maximum or local minimum na to, the way you do it is you get dy over dx is equal to 0. Tama? Ito rin dy over dx is equal to 0. Ganyan, ganyan, ganyan. Hopefully you remember your math, no? So that's how we find local minimums or extremas, no? Yung minimums and maximums. So if we were to find the local itong R star na to that corresponds to this maximum right here, the activation energy, then we just get d delta G over dr and equate that to 0. So if you do that, we end up with an equation that looks like this, no? And this is the equation for the critical radius. So we have R star is equal to 2 gamma SL over delta GV. And itong delta GV, we can further, itong R star, if you put it back into the delta G equation, then you can also, you are also able to find yung required activation free energy, no, which is this one. This is the required activation free energy for you to have, no, sorry, ito pala yung final form. For you to have a stable nuclei. Okay? So again, only stable nuclei will continue the process from nucleation to growth. Kung hindi ka stable yung nuclei mo, it will just redissolve into the melt. Okay? Now, one thing to note about delta GV, yung volume free energy, pwede actually siyang relate with latent heat of fusion, no? So the delta GV is equal to the latent heat of fusion. This is discussed in MetE176, no? So this is the heat associated with the release of heat associated with transformation from liquid to solid, no? And vice versa na kung heat absorbed siya from solid to liquid naman. Okay? So ito, if we multiply that with delta T and divided by the melting point, then we actually get the delta GV, no? And this delta T right here is equal to this value. And this delta T is quite important, no, when we talk about nucleation and growth. Ang tawag natin dito is undercooling, no? Sometimes supercooling. And you probably heard of the term before, no, undercooling or supercooling. It's just the temperature, the amount of difference between the known melting temperature and the working temperature. So usually, um, for you to be able to ano no to accomplish to proceed with solidification, there must be some degree of undercooling, no? Kasi kung wala kang degree of undercooling, maging zero to. So zero yung delta GB mo. So wala kang delta GB. And later makikita natin sa equations din na na kailangan talaga na meron kang degree of undercooling. Pero later you'll find out that um i, lalo na pagka alloys, no, dahil sa mga heterogeneous nucleation, mga and other factors, kahit sobrang late lang ng undercooling, kaya na ma-achieve yung ano. Pero it has been proven in very pure metals, no, that dahil sa pure metals, parang we are expected homogeneous yung nucleation. um Pag homogeneous yung nucleation, there is some degree of undercooling that is required for you to be able to proceed to nucleation. Okay? So ito, yun yung undercooling, and undercooling is represented by delta T, no? And we will be using this term a lot, no? Kahit dun sa later discussions natin, lalabas ng term na undercooling. Okay? So if we substitute the undercooling, itong delta GV with this one, LV times delta T over TM, we will end up with this equation, no? And notice na all of these, itong factors na to or itong variables na to are these are constants. So this is a thermodynamic quantity. This is also a thermodynamic quantity. PM is also a thermodynamic quantity. So the only parang independent variable dito na pwede mong baguhin is actually itong degree of undercooling delta T, no? And same goes with itong sa delta G star, no? So ganyan. So it seems na that R star is inversely proportional with delta T. So what this means is delta T actually is a measure of the ease of which uh, we can form stable nuclei. Because if you look at it, if you increase the delta T, that is saying na you decrease the temperature. Again, this is T melting, no? And this is T. And delta T is equal to Tm minus T. Therefore, kung mas mababa yung temperature mo, you are moving downwards away from the further you are away, the larger this delta T is. Tama? So kung mas malayo ka sa equilibrium melting temperature, mas lumiliit tong R star value na to. Which means that mas konti yung critical radius na kailangan ng nuclei mo para maging stable siya. Tama? So essentially, the larger the delta T, the easier it is to form stable nuclei. And when it's easier to form stable nuclei, mas madali mag-proceed yung solidification process. So that's why yung delta T natin is indicative of the of how fast or how slow the progression of the solidification works, no? Okay? So, yan. Then we can estimate as well, no, yung parang and I won't go into much detail dito, pero you can estimate the nucleation rate as well, and we can relate it with delta T, no? So let's look at how delta T is affected by the nucleation rate. So this is just saying na yung kung ano yung probability that you will encounter a cluster of a particular radius, no? So this is a probability function, and this type of equation is known as an Arrhenius type equation, no? Anytime you see something like A raised to the E, usually ganyan siya, no? Negative type of energy over RT, yung mga ganyan. That's an Arrhenius type equation, no? So this describes kumbaga probabilistic to na equation. So what this says is that if we try to plot the R versus the delta T or degree of undercooling, you'll find out that yung R max natin or the maximum radius na kayang ma-achieve ng mga nuclei natin increases with delta T. Tama? And we've already said earlier that the R star, yung critical radius needed to form stable nuclei, is inversely proportional with delta T. So um, there seems to be a level of degree of undercooling that is required for you to be able to produce a stable nuclei, no? Kasi if you look at this, anything lower than this delta Tn right here, delta T sub n, your R max is smaller than the required R star. So meaning wala talagang kumbaga wala talagang stable nuclei na ma-form dito sa anything below delta Tn. Pero once na nandito ka na, pag ganyan, your R max is now always larger than the R star. So, kumbaga, feel mo na yung requirement. So, yung critical radius mo, kaya na ma-achieve ng R max mo. Okay? So, malapit na yung time, no? So, I'll probably extend mga 2 minutes lang class, no? Tapusin ko lang hanggang heterogeneous nucleation. Pero when we look at this, no, this just says that there seems to be a delta T, a certain degree of undercooling that is required para ma-meet natin yung R star requirement. Okay? Now, this is a complex function, no? Ito hindi ko na go into detail, pero we can estimate the nucleation, the homogeneous nucleation rate by this formula. And ito sila mga complex function siya. This is the delta G over RT. Parang ganun. Negative delta G to, naka-embed na dyan, over T lang ata, wala na atang R. Pero in any case, ano siya, kumbaga, ito, yung simplification, and you'll notice na, etong si delta T, nakapaloob siya sa exponent, no, sa an exponent function, tapos naka-squared pa siya. So what happens is if you try to plot this this function right here, it will seem na parang ganito siya. So parang zero siya, it starts at zero, almost undetectable siya, tapos bigla pagpasok sa delta Tn, biglang magsa-spike up siya, mag-shoot siya sa ng ganyan, yung homogeneous nucleation rate. Tapos parang you can consider this as an explosion of and yung terms na ginagamit ng reference namin is myriad, no, a myriad of nucleation sites. So ang nangyayari diyan is once you achieve the delta Tn, required delta Tn, parang almost instantaneously mag-solidify siya kasi sobrang daming mga nucleation sites na nagiging available. So magsi-start na yung kumbaga sobrang daming stable nuclei, I should say. So sobrang daming stable nuclei na mafo-form, tapos from that stable nuclei magbibigay na yung growth natin. Okay? So ito, I think you can just read this, no, itong mga sample problems. Siguro ang ipo-point out ko lang sa sample problems na to is ang sinasabi lang dito kaya siya number of unit cells per particle is because 'di ba, kung naalala niyo yung unit cell, a unit cell is the smallest na parang non-repeating na pattern na mapoproduce mo from a lattice. Yun yung unit cell natin. Tapos meron siyang yung tinatawag na itong A value, which is the lattice parameter, no? Ito. Hopefully you remember MetE176 lattice parameter. So parang sinasabi dito is ang volume nito is A cube. So ilang A cube ang maipapasok mo doon sa um, nucleus mo of radius R star. So kung meron kang radius na R star dyan, ilang mga stable na, kumbaga parang ganyan, ilang ganito yung kasya dyan sa loob ng stable nuclei dyan. So baka lang malito kayo kung paano nakuha tong number of unit cells. O bakit over A cube natin siya ginawa. So eto ang assumption dito is the hard sphere model to, no. Hopefully you remember what hard sphere model is. Hard sphere model is yung parang ina-assume natin na parang mga marbles itong natin, no. Itong mga kunwari BCC, FCC siya, kunwari ganyan. So ina-assume natin na ito lahat hard sphere siya, no. So parang mga marble, mga Holland. So, parang ganyan. So, if you have the number of unit cells per particle, pwede mo na siya i-multiply by the number of atoms per unit cell. So, for, ano ba to? This is FCC. You need to know kung FCC siya or BCC, no? Pero, if you know the structure kung BCC or FCC, then you know the number of atoms per unit cell. As multiply mo lang, and in this case, it's 4. So 4 times 137, yun yung number of atoms contained in the critical nucleus. Okay? Anyway, tapos, last 2 minutes, sorry class. Ito, sa heterogeneous nucleation, what happens is, you begin, instead of, kasi kung homogeneous nucleation ka, it requires na from the liquid, magpuproduce ka ng solid na sphere, no? Pero what happens in heterogeneous nucleation, meron kang actually yung external surface. So this could be a mold or a additive. And let's just for simplicity sake, kunwari mold siya na ganyan. So if it's a mold, you will produce something that looks like this, no? And ito yung computation natin ng contact angle, if you remember MetE176. And if you do the calculations, you actually can compute for the delta G star and the R star required for this. And it's related with the contact angle, no? So it depends on the contact angle. Pero if you do the calculations, you simplify, actually same lang yung makukuha mo na overall delta G for heterogeneous, no? It's just the delta G, and ito tama to, no? Naka-negative siya. So it's delta G of the homogeneous. So this is actually delta G homogeneous multiplied by itong S S theta, no? Ito, we call this as a shape factor. Shape factor tawag dito. And the shape factor is equivalent to, ito siya. This is the shape factor, no? Depending on the theta. And siguro you can compute for this on your own. To compute this, kailangan i-assume mo na yung mali, pangit yung drawing ko. Dapat ang i-assume mo is parang meron kang spherical cap, no? So parang ganyan, spherical cap siya. So ito yung mold mo, spherical cap. Tapos from the geometry, mako-compute mo na ganito siya. So you'll notice, class, na if you do the the differentiation, yung technique na ginawa natin kanina, since this is just a constant, ang mangyayari actually, you still get the same R star, no? Pero posible ba 'yan? Medyo dito na magiging confusing kasi I mentioned earlier na hindi ba sabi mo sir kanina na ang heterogeneous nucleation should be faster. So it should make sense na dapat yung R star is lower. Tama? That seems logical, no? Pero actually, yung critical radius that is required to create a stable nuclei remains the same. Same lang yung requirement. The only difference is that mas mababa yung activation energy na required. So if we were to plot it, parang, and maybe I'll include a plot here, no? Pero if you were to plot it, parang yung delta G na kailangan for heterogeneous nucleation is significantly smaller, no? Because this shape factor is always less than 1. So itong shape factor na to will never be greater than 1. It's always less than 1. Therefore, delta G star will always be less than 1. So the only case wherein magiging equal sila is if perfectly wettable yung surface, itong solid, such that parang ganyan siya, perfect wetting condition siya. If you remember perfect wetting condition, wherein si theta natin is 180 degrees. Parang ganyan. So, hindi naman nangyayari yon. So, ang dito is, this is always smaller. So, ibig sabihin, yung activation free energy for heterogeneous nucleation is always smaller. Therefore, in that sense, easier pa rin ma-achieve mo yung R star value, yung critical radius. Another way of imagining this is, and we can use this, another way this can be imagined is, same pa rin yung R star value, parang ganyan. Ito pa rin yung R na kailangan mo. So this is still the R star that is required to form the stable nuclei. It's just that a large portion is already filled out by the mold or the external surface. So konti na lang yung atoms na kailangan pumunta dito. Kumbaga inassume na ang a portion of that critical mass is already assumed by the mold. Therefore, konti na lang yung kailangan para maging stable nuclei. So, yun lang muna. I think I'll end the session right here, no? Kasi may mga class pa yung iba. And thank you for taking the time to kahit nag-extend tayo konti, no? So, if you have any questions, pwede naman i-tanong nyo sa akin through email or through Google Chat, or pwedeng kung if you're free, wala kayong ibang other subjects for today, pwede nyo naman itanong ngayon, tapos sagutin ko, tapos para sa mga kailangan umalis, panoorin na lang siguro ang recording. Okay, may questions pa? Wala naman, parang walang question, no? So, yun lang muna. Let's end there sa nucleation and growth, and siguro nucleation lang muna, tapos yung growth i-discuss na lang natin some other time. So, thank you everyone for coming in today, and hopefully mas naliwanagan kayo sa lesson natin today, and we will have more lessons to come sa synchronous session. Right? So, I'll see you. Mag-announce na lang ako kung kailan yung next meeting natin. Alright. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
And bye everyone.
Thank you po.